All right, hello everyone, and welcome to our 9th lesson in Unit 5, which is on pre-equilibrium approximation. In this lesson, we're continuing our work with reaction mechanisms, but now we're focusing on cases where the first elementary step is not the rate-determining step. Sometimes the mechanism begins with a fast reversible step that quickly establishes an equilibrium before the slower step occurs. Even though that first step happens early, it doesn't control the overall rate. The slow step still determines the rate law. The challenge is that the slow step rate law may contain an intermediate, which cannot appear in the final experimental rate law. So in these situations, we use an approximation like the pre-equilibrium approximation to rewrite the intermediate concentration in terms of the original reactants and products, which produce a valid overall rate law. All right, so what happens if the first step in your mechanism is fast and reaches equilibrium? Well, that is when we are using the idea of pre-equilibrium approximation. Now, all of the steps we've learned in the past are still applicable here. The reason I am teaching you this is to explain why we can use those sort of shortcuts. So a pre-equilibrium approximation is going to assume that for that fast equilibrium step, the rate of the forward reaction is going to be equal to the rate of the reverse reaction. This means that we can set the two rate laws, the forward and the backward, equal to each other, which allows us to solve for the intermediate and substitute it into the rate law for the slow step. So here we have a two-step mechanism where the first step is fast and the second step is slow, meaning the second step is our rate determining step. So when we are starting to build rate law, we're going to focus on the reactants in the slow step, which are NO and NOBr2, and we're going to identify any intermediates. In this case, we have NOBr2 as our intermediate because it is created in step number 1 and consumed in step number 2, and it is nowhere else in the mechanism. So that is our intermediate. So then to build our rate law, we have our remaining reactants. So it will be rate equals K times the concentration of NO raised to the second power, because there are two of them, and Br2 raised to the first power, because there's only one. Now, what is different? What I want to go over today is the idea of if we have a leftover product in our first elementary reaction, you are now going to put that product in the denominator of your rate law. So that's really the only thing we are adding in what we've already learned so far in terms of getting rate from reaction mechanisms. So here's another example of the ones that we have been doing in class. So we see that our slow reaction is step number 2 in the mechanism, and we have N2O2, which is present as a product in step 1. You can also tell that N2O2 is not present in any other steps, so this is for sure an intermediate. And then we are left with H2 as a reactant and NO as a reactant. So if we were to write the rate law for this mechanism, it would be rate equals K times the concentration of H2, and I only have one of those, and the concentration of NO, and I have two of those. So that would be my proposed rate law. All right, so for this example, we can see our step 2 is still our rate determining step. We can see that N2HO2 minus is also present as a product in step 1, and it is nowhere else in the mechanism. So this is our intermediate. So now what we have left before the reactants of step 2 is a product, H+, and our original reactant, N2H2O2. So when we are writing our proposed rate law, we are going to write rate equals K times the concentration of our reactant, N2H2O2, And then we are going to put our product, concentration of H plus, in the denominator. And that would be our proposed rate law for this mechanism. All right, and let's just do a few more examples so that we can make sure we understand how to get rate law from these types of reactions. It says we have a proposed mechanism for the following reaction. Which of the following rate laws is consistent with this mechanism? So this is typically a multiple choice question that I turned into an FRQ. So let's go ahead and get the rate law from this mechanism. So we can see that step number 2 is our rate determining step. We are going to look at our reactants and see if any of them cancel out with our product from step 1, which in this case it does. We also can see that NO2F2 does not present itself anywhere else in the mechanism, so this is for sure an intermediate, which means when we are writing our rate law is going to be rate equals concentration of NO2 times the concentration of F2, and that would be our proposed rate law, and I almost forgot K, don't forget K. And then a question that one student asked me yesterday was, if the first step in this specific example was the rate determining step, would the rate law be the same? And my answer is yes, the rate law would be the same if step 1 was our slow reaction, because we would get the same rate law only looking at the products of step 1. We have 1 NO2 and 1 F2, so it would be the exact same rate law if step 1 was slow. And then our final example for the chemical reaction represented above, the following mechanism is proposed. What is a rate law expression consistent with this proposed mechanism? So again, we can see our step 2 is our slow reaction. So we're going to look at our reactants here. We can see that N2O2 is created in step 1 and used up in step 2, and it's nowhere else in the mechanism, so that's our intermediate. And then we are left with H2 and 2 NOs. So our rate law is going to be rate equals K times the concentration of NO squared times the concentration of H2, and that is our proposed expression. All right, nice short video for today. I hope that helped. Have a great day.